a massive golden star blazing in the center of a vast stellar nursery, surrounded by swirling clouds of luminous gas and cosmic dust. Deep space stretching endlessly in all directions. 4.5 billion years ago, in a quiet corner of our galaxy, something remarkable began to happen. A cloud of gas and dust, floating peacefully in the darkness between stars, started to collapse under its own gentle pull. Enormous clouds of glowing hydrogen, gas slowly contracting inward, brilliant threads of light weaving through the collapsing material. Starlight from distant suns illuminating the cosmic dance. This cloud was massive beyond imagination. It contained enough material to build not just our sun, but our entire solar system. Gravity worked its patient magic. The cloud grew smaller and denser, spinning faster as it shrank. A swirling disk of glowing matter rotating around a bright central core. Golden and orange light streaming through spiraling arms of cosmic dust. At the very center, temperatures began to climb. The pressure mounted. Hydrogen atoms pressed closer and closer together until something extraordinary happened. Nuclear fusion ignited for the first time. A newborn star suddenly bursting into brilliant golden light. Waves of energy radiating outward through space, illuminating nearby clouds of gas in soft blues and purples. Our sun was born in that moment of first light. The nuclear fire that began burning then has never stopped. Every second since that ancient beginning, the sun has been fusing hydrogen into helium in its core. This process releases the energy that warms our planet and makes life possible. If you're enjoying these facts so far, go ahead and hit that like button and subscribe. A brand new topic drops every single night to help you drift off to sleep. A brilliant golden comet trailing a luminous glowing tail through a vast purple nebula. Stars and cosmic dust swirling around. Epic deep space vista. Cinematic lighting. Fantasy art style. Dreamy and majestic. The sun's glowing surface rippling with waves of superheated plasma. Bright yellow and orange flames dancing across the stellar atmosphere. Solar prominences arcing into space. The sun weighs as much as 333,000 Earths combined. Its mass is so enormous that it makes up more than 99% of everything in our solar system. All the planets, moons, asteroids, and comets together account for less than 1% of the total mass. 8 planets orbiting in perfect circles around a blazing central star. Each world a tiny speck compared to the massive golden sun at the center. Layers of glowing plasma swirling within a cross-section view of a star. The bright core radiating intense white light, surrounded by zones of yellow and orange energy. Inside the sun, temperatures reach 27 million degrees Fahrenheit. The pressure at the core is 250 billion times stronger than the air pressure we feel on Earth. Under these extreme conditions, hydrogen nuclei overcome their natural tendency to repel each other and fuse together. Brilliant white light streaming outward from a star's core, passing through layers of glowing gas. The energy slowly working its way toward the surface. Each fusion reaction converts a tiny amount of matter into pure energy, following the famous equation that energy equals mass times the speed of light squared. Golden sunlight streaming through space toward a blue marble planet. The warm rays illuminating one hemisphere while the other rests in peaceful darkness. The light leaving the sun's surface right now began its journey in the core hundreds of thousands of years ago. Photons of light bounce randomly through the dense interior, taking an incredibly long time to reach the surface. Once they break free, they race across space at 186,000 miles per second, reaching Earth in just over 8 minutes. A massive golden sphere of plasma floating in the black void of space, its surface churning with waves of brilliant fire, solar flares arcing gracefully into the darkness. Our sun is what astronomers call a yellow dwarf star. This name feels almost silly when you consider the reality. The sun contains 99.86% of all the mass in our entire solar system. If Earth were the size of a marble, the sun would be a beach ball 9 feet across. Glowing yellow plasma swirling across a star's surface, magnetic field lines, visible as bright loops of energy dancing above the burning sphere. The sun weighs about 333,000 times more than Earth. To put this in perspective, you could fit 1.3 million Earths inside the sun's volume. Yet in In the grand scheme of the galaxy, our sun ranks as perfectly average. Half of all stars are smaller and dimmer. Half are larger and brighter. A cross-section view of a star showing layers of different colored plasma. From the white-hot core to the golden outer regions, energy radiating outward. The sun stretches 864,000 miles across its middle. This means you could line up 109 Earths side by side across the sun's diameter. Light takes about 4.5 seconds to travel from one side of the sun to the other. The same beam of light crosses Earth's diameter in just 43 milliseconds. A brilliant star burning steadily in deep space, surrounded by swirling clouds of cosmic dust and gas. The stellar wind pushing particles outward in all directions. Our star formed roughly 4.6 billion years ago from a collapsing cloud of gas and dust. The sun has been burning steadily ever since, converting hydrogen into helium in its core. Every second, the sun transforms 600 million tons of hydrogen into helium through nuclear fusion. Streams of golden light radiating outward from a luminous star. The photons traveling through the vacuum of space toward distant worlds. This process releases tremendous energy. The sun produces more energy in 1 second than humanity has used in all of recorded history. The core temperature reaches 27 million degrees Fahrenheit. The surface, which we can actually see, runs a cooler 10,000 degrees. A majestic view of the sun's corona. Wispy tendrils of superheated plasma extending millions of miles into space, glowing with ethereal silver light. The sun's atmosphere extends far beyond its visible surface. The corona, that ghostly halo we see during eclipses, stretches millions of miles into space. This outer atmosphere burns at over 2 million degrees, mysteriously hotter than the surface below. Solar plasma flowing in complex patterns across a star's surface, bright magnetic loops connecting different regions, creating of golden fire. The sun spins on its axis, but not like a solid ball. The equator completes one rotation every 25 days. The poles take 35 days to spin around once. This uneven rotation creates the complex magnetic fields that drive solar weather. a cutaway view showing the sun's internal structure, with the blazing white core surrounded by zones of convecting yellow plasma carrying energy upward. Inside the sun, energy moves outward through two main zones. The radiation zone surrounds the core, where photons bounce randomly for thousands of years. Above that lies the convection zone, where hot plasma rises and cooler plasma sinks, like water boiling in a pot. Brilliant white light emerging from a star's photosphere, the visible surface layer glowing with intense heat, granules of plasma creating texture across the burning sphere. The photosphere forms the sun's visible surface. This layer is only about 300 miles thick, thinner than the distance between major cities. Below the photosphere, the sun becomes opaque. Above it, the atmosphere grows transparent, a panoramic view of the sun floating in space, its golden radiance illuminating nearby cosmic dust, the star appearing both powerful and serene against the infinite darkness. From Earth, the sun appears to move across our sky, but this motion comes from our planet's rotation. The sun actually travels through the galaxy at 450,000 miles per hour, carrying our entire solar system along for the ride. We orbit the galactic center once every 230 million years. A vast molecular cloud floating in the darkness of space, dense with cosmic dust and hydrogen gas, glowing faintly from the light of distant stars scattered throughout the galaxy. Long before the sun existed, a giant cloud of gas and dust drifted through space. This cloud contained mostly hydrogen, the simplest element in the universe. For millions of years, it floated peacefully through the galaxy, cold and dark, shock waves rippling through a nebula, bright energy pulses spreading outward from an exploding star, disturbing the quiet gas and dust in luminous waves of blue and gold. Then something disturbed this quiet cloud. Scientists believe a nearby star exploded in a supernova. The shock waves from this explosion pushed through the gas cloud like ripples in a pond. A cosmic cloud beginning to collapse inward, swirls of gas and dust spiraling toward a growing center, the material glowing softly as it compresses and heats. The shock waves caused parts of the cloud to become denser, Gravity began pulling these dense regions together. As more material gathered, the pull of gravity grew stronger. The early solar nebula spinning faster, a flat disk of glowing gas and dust with a bright hot center forming, spiral arms of material feeding into the growing core. The collapsing cloud started spinning faster and faster, just like an ice skater pulling in their arms. This spinning motion flattened the cloud into a disk shape. At the center of this disk, matter piled up into a growing ball of gas, a protostar glowing deep red in the center of a swirling disk, not yet hot enough for fusion, surrounded by rings of dust and gas that will become planets. This central ball became what astronomers call a protostar. It was not yet a real star because it could not make its own light. For about 50 million years, the protostar grew larger and hotter as more gas fell onto it. The interior of a forming star heating up, layers of compressed hydrogen gas glowing brighter and brighter, temperature rising toward the critical point of nuclear fusion. Deep inside, the temperature climbed higher and higher. The pressure became enormous. Hydrogen atoms were squeezed together so tightly they could barely move. The moment nuclear fusion ignites in a star's core, brilliant white light erupting from the center as hydrogen atoms fuse into helium, marking the birth of a true star. Finally, when the core reached 18 million degrees Fahrenheit, something magical happened. Hydrogen atoms began fusing together to form helium. This process released tremendous amounts of energy. The sun had been born, a newly formed sun blazing to life, its surface erupting with golden flames and plasma jets. The surrounding disk of planetary material glowing in the star's first light. The nuclear fusion in the core created outward pressure that balanced the inward pull of gravity. This balance allowed the sun to shine steadily. The young sun's powerful stellar wind blowing away leftover gas and dust from the solar system. Streams of charged particles flowing outward like invisible rivers of energy. The newborn sun was much more active than it is today. Its stellar wind blew away most of the leftover gas from the original cloud. Rocky debris and ice chunks orbiting the young sun. The building blocks of planets slowly clumping together in the clear disk around the blazing new star. Only the heavier materials like rock and metal remained close to the sun. These materials would eventually clump together to form the rocky planets, including Earth, the sun settling into its main sequence phase, burning steadily with a warm golden glow. Having found the perfect balance between gravity pulling inward and fusion pushing outward. After about 100 million years of formation, the sun settled into the steady burning phase it maintains today. It had found the perfect balance between the crushing force of its own gravity and the explosive power of nuclear fusion at its heart. Sun burns because it transforms the simplest element in the universe into something more complex. Brilliant streams of hydrogen, nuclei colliding and fusing in the sun's blazing core, releasing bursts of pure energy that illuminate the surrounding plasma. Deep in the core, hydrogen atoms slam together with such force that they merge into helium. This process creates the energy that lights our world. Every second, the sun converts about 600 million tons of hydrogen into helium. The missing mass becomes pure energy that eventually reaches Earth as sunlight. Hydrogen makes up about 73% of the sun's total mass. Vast clouds of glowing hydrogen gas swirling through the sun's outer layers, painted in shades of gold and orange by the intense heat. This hydrogen came from the same ancient cloud that formed our entire solar system. Helium accounts for most of the remaining mass, about 25%. The sun also contains traces of heavier elements like oxygen, carbon, nitrogen, and iron. Scientists call these heavier elements metals, even though some are gases at the sun's temperature. Tiny specks of iron floating in the sun's chromosphere, glowing red hot against the backdrop of swirling solar plasma. The iron in the sun tells an ancient story. This metal was not created during the sun's formation. Instead, it was forged in the nuclear furnaces of massive stars that lived and died billions of years ago. When those giant stars exploded as supernovas, they scattered their iron across space. A supernova explosion blooming like a cosmic flower, ejecting streams of glowing metals and heavy elements into the surrounding nebula. That scattered iron eventually became part of the gas cloud that collapsed to form our sun. The same process happened with all the heavier elements in the sun. Glowing wisps of carbon and oxygen drifting through the sun's outer atmosphere, their atoms forged in the hearts of ancient stellar giants. The calcium, silicon, and magnesium in the sun were all created by nuclear fusion in stars that died before our solar system existed. These elements make up less than 2% of the sun's mass, but they connect our star to the cosmic cycle of stellar birth and death. Every atom heavier than hydrogen and helium in the sun is recycled stardust. Magnetic field lines arcing gracefully above the sun's surface. Invisible forces made visible as glowing plasma follows their twisted paths. The sun's magnetic field emerges from the movement of electrically charged plasma deep inside the star. As the sun rotates, this hot plasma moves in complex patterns that generate magnetic fields thousands of times stronger than Earth's magnetic field. These invisible forces shape the sun's atmosphere and drive many of its most dramatic activities. The magnetic field lines stretch and twist as different parts of the sun rotate at different speeds. Brilliant solar prominences erupting from the sun's edge, following curved magnetic field lines that arch hundreds of thousands of miles into space. The sun's equator completes one rotation in about 25 Earth days, while the polar regions take about 35 days. This difference in rotation speed winds up the magnetic field lines like rubber bands being twisted. When these field lines snap and reconnect, they release enormous amounts of energy. The sun's convection zone churning with massive cells of rising hot plasma, each cell larger than Earth, creating a bubbling pattern across the solar surface. Below the sun's visible surface lies a region where hot plasma rises like bubbles in boiling water. These convection currents carry energy from the core toward the surface. Each convection cell spans thousands of miles and lasts for weeks or months. The rising hot plasma carries magnetic field lines with it, creating the complex magnetic patterns we observe on the sun's surface. The sun's magnetic field reverses completely about every 11 years. Streams of charged particles flowing outward from the sun in all directions following the invisible magnetic field lines that extend throughout the solar system. During this magnetic flip, the sun's north magnetic pole becomes its south pole, and the south becomes the north. This reversal affects the entire solar system because the sun's magnetic field extends far beyond the planets. The solar wind carries this magnetic field to the very edges of our cosmic neighborhood, creating a vast magnetic bubble around all the planets. The boundary where the sun's magnetic influence meets interstellar space, marked by a glowing shock wave as solar particles encounter the cosmic medium. Scientists have discovered that the sun's magnetic field creates a protective barrier around our solar system. This barrier, called the Heliosphere, shields us from some of the high-energy particles that travel between the stars. The magnetic field embedded in the solar wind helps deflect cosmic rays that could otherwise reach Earth's atmosphere. Without this protection, life on Earth would face much higher levels of dangerous radiation from deep space. The sun's magnetic forces create storms so powerful they can disrupt satellites orbiting Earth thousands of miles away. Brilliant orange and yellow plasma erupting from the sun's surface in towering loops, following invisible magnetic field lines against the deep black of space. When magnetic field lines on the sun's surface become twisted and tangled, they store enormous amounts of energy. These twisted fields can suddenly snap back into place, releasing energy equal to billions of nuclear bombs in just a few minutes. The explosion sends waves of charged particles racing through space at millions of miles per hour. Solar flares represent some of the most violent events in our solar system. A massive burst of white-hot plasma shooting outward from the sun's chromosphere, creating brilliant streamers of light that extend far into the surrounding darkness. The largest flares can be seen from Earth as bright flashes near sunspots. These eruptions heat the surrounding solar atmosphere to temperatures of 20 million degrees. That heat is so intense, it would vaporize any known material in seconds. The energy from a single large flare could power the entire United States for millions of years. Coronal mass ejections carry even more material into space than solar flares. An enormous bubble of glowing plasma expanding outward from the sun, carrying twisted magnetic field lines and billions of tons of solar material through the solar wind. These eruptions can launch 1 billion tons of solar material into space at speeds of several million miles per hour. When this material reaches Earth, it can cause the northern lights to appear as far south as Florida. The charged particles interact with our planet's magnetic field, creating those dancing curtains of green and blue light in the night sky. The sun's magnetic field controls where these storms occur and how intense they become. Swirling patterns of magnetic energy, visible as dark and bright regions across the sun's glowing surface, with arcing plasma following the field lines. Areas where magnetic field lines emerge from inside the sun appear as dark sunspots because they block some of the heat from reaching the surface. The strongest magnetic fields can be 4,000 times more powerful than Earth's magnetic field. These intense magnetic regions act like pressure cookers, building up energy until it explodes outward in spectacular fashion. Sometimes the sun launches multiple storms in quick succession, creating what scientists call a solar storm train. 3 successive waves of bright plasma erupting from different regions of the sun's surface, each wave larger than Earth, racing outward in a chain of solar fury. These storm trains can batter Earth's magnetic field for days or weeks. During particularly intense storms, the charged particles can penetrate deeper into our atmosphere than usual. This can disrupt radio communications and damage sensitive electronics on spacecraft and even on the ground. The pressure from solar storms can actually compress Earth's magnetic field on the side facing the sun. Earth's blue magnetic field lines being pushed inward by invisible solar wind pressure, creating a teardrop shape around the planet with a long tail extending away from the sun. This compression can squeeze our magnetic field so tightly that it snaps back like a rubber band. When it snaps back, it sends particles racing toward Earth's poles at incredible speeds. These particles collide with oxygen and nitrogen in our upper atmosphere, making them glow with the colors we see as auroras. The sun's storms follow the same 11-year cycle as the magnetic field reversals. A time-lapse view showing the sun's surface changing from calm and smooth to covered with bright active regions and dark sunspots over several years. During solar maximum, when the sun is most active, dozens of flares and coronal mass ejections can occur each day. During solar minimum, the sun might go weeks without producing a single major storm. This cycle affects everything from satellite operations to the growth rings in trees on Earth. Even during quiet periods, the sun constantly sends smaller streams of charged particles in all directions. Gentle streams of golden particles flowing outward from every part of the sun's surface, creating a steady wind that fills the entire solar system with soft, glowing light. This solar wind travels at about 1,000,000 miles per hour and takes about 4 days to reach Earth. The wind carries pieces of the sun's magnetic field with it, creating magnetic highways that connect our star to every planet in the solar system. These invisible connections mean that storms on the sun can affect the entire cosmic neighborhood we call home. The solar wind that streams from our sun never stops flowing. An endless river of golden particles streaming outward from the sun's glowing surface, spreading in all directions through the darkness of space like luminous mist. This invisible wind fills a bubble around our solar system that stretches 4 times farther than Pluto. Scientists call this bubble the Heliosphere. If you could see it from outside, our entire solar system would look like a glowing soap bubble drifting through the galaxy. The scale of this wind is almost impossible to grasp. Every second, the sun loses 4 million tons of its own mass by sending particles into space. Massive streams of bright particles erupting from the sun's surface and flowing outward past glowing planets, creating highways of light through the solar system. That sounds like a lot, but the sun is so enormous that it would take 150 billion years to lose just 1% of its mass this way. The sun has enough material to keep blowing this wind for trillions of years. To understand how far this wind travels, imagine shrinking our solar system. If the sun were the size of a basketball, Earth would be a peppercorn sitting 26 yards away. A brilliant orange sphere surrounded by tiny glowing specks at vast distances, connected by flowing streams of light that stretch far beyond the visible edge. Mars would be a pinhead 40 yards from the basketball sun. Jupiter would be a marble 135 yards away. At this scale, the solar wind would fill a sphere stretching more than 2 miles in every direction from the basketball sun. The wind moves incredibly fast. At 1 million miles per hour, it could circle Earth in just 2.5 minutes. Waves of shimmering particles racing through space at tremendous speed, leaving trails of golden light as they pass by distant planets and moons. Yet space is so vast that this 1,000,000-mile-per-hour wind still takes 4 days to travel from the sun to Earth. It takes more than a year to reach the outer planets. The solar wind carries about 5 billion tons of material past Earth every day. An enormous invisible river of glowing particles flowing past a blue and white planet. The streams curving around the planet's magnetic field like water around a stone. That might sound like Earth should be getting buried under all these particles. But space is so empty that this massive flow creates a pressure no stronger than the light from a small flashlight. The solar wind is incredibly thin. Each cubic inch of space near Earth contains only about 5 particles from the solar wind. When this wind reaches the edge of our solar system, it crashes into the interstellar medium, a vast glowing boundary where golden solar wind particles meet the darker particles of deep space, creating swirling patterns of light and shadow. This creates a shock wave called the heliopause. Beyond this boundary, the solar wind can no longer push against the material between stars. Our sun's influence ends, and true interstellar space begins. The solar wind shapes the tails of comets. A bright comet with twin tails streaming away from the sun. One tail made of glowing gas particles, the other of sparkling dust, both swept back by invisible solar wind. When a comet approaches the sun, the solar wind blows the comet's gas and dust away from the sun, creating those beautiful tails that always point away from our star. The wind is so persistent that comet tails can stretch for millions of miles. This endless wind connects every world in our solar system to the sun. Invisible threads of light connecting a central glowing star to all the planets around it, creating a web of energy that spans the entire cosmic neighborhood. The magnetic field carried by the solar wind creates space, whether that affects satellites, radio communications, and the beautiful auroras that dance in our skies, even on the calmest days, when the sun appears peaceful and quiet. This wind continues its ancient journey outward, carrying pieces of our star to the very edges of the solar system and beyond. The light that warms your face on a sunny morning began its journey 8 minutes and 20 seconds ago. A brilliant golden sphere of plasma suspended in the cosmic void, its surface rippling with waves of superheated gas that glow like molten honey. Deep inside the sun's core, nuclear fusion creates photons of light that must travel 93 million miles to reach Earth. This distance seems vast, but light moves so quickly that it could circle our entire planet 7.5 times in just 1 second. The sun's surface temperature reaches about 10,000 degrees Fahrenheit. Towering columns of plasma erupting from a blazing stellar surface, each pillar stretching higher than 10 Earths stacked on top of each other. This outer layer, called the photosphere, creates the golden glow we see when we look at our star. The photosphere bubbles and churns like a pot of boiling water. But instead of water, it's made of hydrogen and helium gas heated to temperatures that would vaporize any known material. Giant cells of hot gas rise and fall across the sun's surface in a pattern called granulation, the textured surface of a star showing thousands of bright cellular patterns, each cell glowing white-hot at the center and darker orange at the edges, creating a honeycomb of fire. Each granule measures about 600 miles across and lasts for only 8 to 20 minutes before it cools and sinks back down. New granules constantly form as hot gas rises from deeper layers, creating a surface that never stops moving. The sun rotates, but not like a solid ball. Swirling bands of golden plasma flowing at different speeds across a massive stellar sphere, creating spiral patterns of light and shadow. The equator spins faster than the poles, completing one rotation in about 25 days, while the polar regions take 35 days to make the same journey. This difference in rotation speed twists and tangles the sun's magnetic field lines, creating the complex patterns that drive solar storms and sunspots. Sunspots appear as dark patches on the sun's surface, but they're only dark compared to their surroundings. Dark circular regions dotting a brilliant solar surface, each spot surrounded by bright penumbral filaments that spiral inward like cosmic whirlpools. These spots still glow at temperatures of about 6,000 degrees Fahrenheit. They form where strong magnetic fields push up through the photosphere, cooling the gas and making it appear darker. Some sunspots grow larger than Earth itself and can last for weeks or even months. Above the photosphere lies the chromosphere, a thin layer of gas that glows with a reddish light, a thin crimson shell of glowing gas surrounding a golden star, with delicate spicules of red plasma shooting upward like cosmic grass, swaying in an invisible breeze. This layer gets its name from the Greek word for color, and it's only visible during solar eclipses when the bright photosphere is blocked. The chromosphere reaches temperatures of about 14,000 degrees Fahrenheit, making it actually hotter than the surface below it. Spicules rise from the chromosphere like blades of grass made of fire. Thousands of needle-thin jets of rose-colored plasma shooting upward from a stellar surface, each jet reaching heights that dwarf mountain ranges on distant worlds. These jets of hot gas stretch upward for thousands of miles, lasting only 5 to 10 minutes before they fade away. Scientists count about 3 million spicules covering the sun at any given time, constantly forming and disappearing in an endless dance of plasma and magnetic force. The sun's surface produces different types of light waves, from radio waves to X-rays, invisible waves of energy radiating outward from a luminous star in all directions, creating ripples in space itself that carry light and heat to distant worlds. Most of the light we see falls in the visible spectrum, the same colors we observe in a rainbow. The sun produces more yellow and green light than any other color, which is why our star appears yellow-white to our eyes. This light carries the energy that powers photosynthesis in plants and drives weather patterns across our planet. Solar flares occasionally burst from the sun's surface, with incredible violence. A massive arc of brilliant white plasma erupting from a solar surface, the flare stretching across space in a graceful curve that could encompass several Earth-sized worlds. These explosions release as much energy as billions of hydrogen bombs detonating simultaneously. The light from a solar flare can brighten the sun's appearance and create radio blackouts on Earth within minutes of the eruption. Prominences arch high above the sun's surface, following invisible magnetic field lines. Graceful loops of glowing red plasma suspended above a golden stellar surface, each arch following curved magnetic pathways that stretch across cosmic distances. These structures can remain stable for days or weeks, held in place by the sun's magnetic field. When they collapse, they rain hot gas back down onto the surface in spectacular displays that dwarf any earthly waterfall. Some prominences stretch so high that dozens of Earths could fit beneath their towering arcs. The boundary between the sun and space isn't sharp like the edge of a solid planet. The fuzzy edge where a brilliant star gradually fades into the darkness of space, with tendrils of light and plasma extending far beyond the visible surface. Instead, the sun's atmosphere extends millions of miles outward, growing thinner and hotter as it reaches toward the stars. This creates a gradual transition from the dense, visible surface to the nearly empty vacuum of interplanetary space, where the solar wind begins its endless journey to the edges of our cosmic neighborhood. Deep beneath the sun's brilliant surface lies a hidden world that follows its own mysterious rhythm. Cross-section view of a golden star revealing layered depths, with the bright core glowing white-hot, while darker regions swirl in complex patterns beneath the luminous surface. The sun's magnetic field doesn't stay the same from year to year. Instead, it flips completely upside down every 11 years in a cycle that scientists call the solar maximum and solar minimum. During solar minimum, the sun appears calm and quiet. Sunspots nearly disappear from its surface, a serene golden sphere hanging in space, its surface smooth and unmarked, radiating gentle light without the dark blemishes of active periods. The magnetic field lines run in neat, orderly patterns from the North Pole to the South Pole, solar flares become rare events. The sun's corona shrinks closer to its surface, creating a smaller, more compact atmosphere. But this peaceful time doesn't last forever. As the cycle progresses toward solar maximum, everything changes. A turbulent stellar surface covered in dark magnetic knots and bright active regions, with twisted field lines creating chaotic patterns across the golden sphere. The sun's magnetic field begins to tangle and twist like invisible ropes being wound too tightly. Sunspots multiply across the surface in growing numbers. The magnetic field lines stretch and snap, releasing enormous amounts of energy. At solar maximum, the sun becomes a restless giant. Brilliant white-hot plasma erupting from a star's surface in towering columns, each fountain of light reaching heights that dwarf planetary dimensions. Solar flares burst from active regions almost daily. The corona expands outward, growing larger and more complex. Prominences dance along magnetic field lines like cosmic auroras, frozen in slow motion. The 11-year cycle affects more than just the sun's appearance. Streams of charged particles flowing outward from a glowing star, creating invisible rivers of energy that stretch across the darkness of space. The solar wind grows stronger during active periods, carrying more charged particles toward Earth. Our planet's magnetic field deflects most of these particles, but some slip through to create more frequent and intense auroras. Scientists have tracked this cycle for centuries by counting sunspots, a golden stellar surface dotted with small dark regions, each spot surrounded by brighter areas that glow like tiny suns within the greater fire. Ancient Chinese astronomers noticed these dark patches over 1,000 years ago. Modern telescopes reveal that each sunspot is actually cooler than the surrounding surface, appearing dark only by comparison to the blazing brightness around it. The cycle's timing isn't perfectly regular. Some cycles last only 9 years, while others stretch to 13. Magnetic field lines, visualized as glowing threads of blue and gold light, weaving complex patterns above a star's surface before suddenly snapping and reorganizing. The strength of each maximum varies too. Some peaks bring hundreds of sunspots, while others produce only a few dozen. Scientists still don't fully understand what controls these variations. During the deepest solar minimums, the sun can go months without a single visible sunspot, a perfectly smooth golden orb floating in the cosmic void, its surface unmarked and serene, radiating steady light like a celestial lighthouse. These quiet periods allow astronomers to study the sun's base structure without the chaos of magnetic storms. The corona becomes simpler and more symmetrical, revealing the underlying patterns that active regions normally hide. But even during minimum, the sun never truly sleeps. Subtle waves of energy rippling across a star's surface, creating gentle patterns of light and shadow that flow like golden water. Deep inside, nuclear fusion continues at the same steady rate. The core temperature remains constant at 15 million degrees. Energy produced today in the sun's heart will take thousands of years to work its way to the surface and finally escape as the sunlight that warms our world. The sun's 11-year rhythm creates one of nature's most dramatic spectacles when it aligns perfectly with the moon's orbit around Earth. A brilliant golden corona streaming outward from behind a dark circular silhouette. Delicate tendrils of plasma dancing in space like celestial flames. Solar eclipses happen roughly every 18 months somewhere on Earth. But any single location might wait centuries to witness totality. The moon's shadow races across our planet at over 1,500 miles per hour, turning day into night in mere minutes. During totality, the sun's hidden corona becomes visible to the naked eye. Gossamer streams of silver and pearl light flowing outward from a black disk, creating intricate patterns against the deep purple twilight sky. This ethereal atmosphere extends millions of miles into space, hotter than the sun's surface, yet invisible except during these precious moments of alignment. The corona's shape changes with the solar cycle. During solar maximum, it appears roughly circular, with streamers reaching in all directions. A perfect ring of blazing white light surrounding complete darkness, with symmetrical plumes of energy extending outward like the petals of a cosmic flower. During solar minimum, the corona becomes more elongated, with long streamers flowing from the sun's equator and shorter plumes near the poles. Ancient civilizations tracked these celestial events with remarkable precision. The Babylonians could predict eclipses hundreds of years in advance, using careful observations of the moon's changing position. Stone monuments arranged in perfect circles on a windswept plain, their shadows pointing toward specific positions where the sun and moon will dance. They understood that eclipses follow an 18-year, 11-day cycle called the Saros. This pattern occurs because 3 different lunar cycles almost perfectly align after this period. The moon completes exactly 223 lunations, passes through the same number of eclipse seasons, and returns to nearly the same distance from Earth. The sun's magnetic field reverses completely every 11 years, marking the true length of the solar cycle. Invisible field lines stretching across space like a vast web, slowly twisting and reorganizing as a star rotates beneath them. Scientists measure this reversal by watching how solar wind particles spiral outward from the sun. During field reversals, the heliosphere becomes turbulent and chaotic. Cosmic rays from deep space find it easier to penetrate the solar system during these transition periods. High-energy particles streaming between the stars, their paths bending and weaving as they encounter shifting magnetic barriers. This affects Earth's atmosphere and may influence cloud formation patterns. The sun's rotation creates another important cycle. Different parts of the sun spin at different speeds, with the equator completing one rotation in about 25 days, while the poles take 35 days. A massive golden sphere slowly turning in space, its equatorial regions moving faster than its polar caps, creating swirling patterns of light and energy. This differential rotation winds up magnetic field lines like rubber bands, storing enormous amounts of energy that eventually explode outward as solar flares and coronal mass ejections. Even the sun's brightness follows subtle cycles. A star pulsing gently with waves of golden light, its luminosity rising and falling in slow, steady rhythms across cosmic time. The total solar irradiance varies by about 0.1% over the 11-year cycle. This tiny change affects Earth's climate in measurable ways. Satellite measurements show the sun grows slightly dimmer during solar minimum and brighter during maximum. Delicate instruments floating in the void of space. Their sensors detecting minute changes in stellar radiation across the electromagnetic spectrum. Tree rings, ice cores, and lake sediments preserve records of these solar cycles stretching back thousands of years, revealing how our star's rhythms have influenced Earth's climate throughout history. The sun does not burn alone in the vast emptiness of space. A brilliant golden star surrounded by a family of 8 worlds, each one following its own graceful orbital path through the cosmic void. Our star sits at the heart of a complex neighborhood where gravity weaves invisible threads between every object. The planets dance around the sun in paths that have remained stable for billions of years, each world held in perfect balance by the star's immense gravitational pull. Mercury races closest to our star, completing its orbit in just 88 Earth days. A small, cratered world glowing silver gray in intense starlight, its surface baked by temperatures that could melt lead. The innermost planet experiences the sun's gravity so strongly that it moves through space at nearly 30 miles per second. Venus follows next, shrouded in thick clouds that trap the sun's heat so effectively that its surface reaches temperatures of over 800 degrees. A pearl-white sphere wrapped in swirling layers of sulfuric acid clouds, glowing softly in the golden light of its parent star. Earth occupies the perfect distance from the sun, where liquid water can exist on its surface, a blue marble suspended in space, its continents painted brown and green white clouds spiraling across azure oceans. Our planet receives just the right amount of solar energy to maintain the delicate temperature range that life requires. Mars orbits farther out, where the sun's warmth grows weaker, and the red planet's thin atmosphere cannot hold enough heat to keep water liquid. A rusty red world dotted with ancient impact craters, polar ice caps gleaming white at its northern and southern extremes. Beyond Mars lies the asteroid belt, a ring of rocky debris that never formed into a planet. Thousands of gray and brown chunks of stone and metal drifting in a vast ring around the distant golden sun. Jupiter's massive gravity stirred this region so violently that the asteroids could never gather together into a single world. The giant planet itself orbits much farther from the sun, where temperatures drop to nearly 300 degrees below zero. A colossal sphere banded with swirling storms of orange, brown, and cream. Its great red spot spinning like a massive hurricane. Saturn glides through space even farther from the sun's warmth, adorned with rings made of countless ice particles, a golden yellow globe surrounded by brilliant rings that catch and scatter starlight into rainbow colors. The sun appears only as a bright star from Saturn's distance, providing barely enough energy to warm the planet above absolute zero. Uranus and Neptune orbit in the outer darkness, where the sun's light takes hours to arrive and provides almost no heat. Two ice blue worlds hanging in the deep cold of space, their surfaces glowing faintly in the distant light of their parent star. The sun's influence extends far beyond the planets through the solar wind, a stream of charged particles that flows outward in all directions, invisible rivers of energy streaming away from a brilliant star, carrying magnetic fields and particles across billions of miles of empty space. This stellar breeze creates a vast bubble around our solar system called the Heliosphere. The solar wind pushes against the thin gas between stars, creating a boundary where our sun's domain meets interstellar space, an enormous glowing sphere of influence surrounding the solar system, its edges rippling where stellar winds meet the cosmic void. Comets provide dramatic evidence of the sun's far-reaching power, a dirty snowball with a brilliant tail of ice and dust streaming away from the approaching warmth of a distant star. These ancient visitors from the outer solar system develop their spectacular tales only when they venture close enough for the sun's heat to vaporize their ice. The solar wind then pushes this vaporized material away from the comet, creating tails that always point away from the sun. A glowing comet with twin tails of blue iron gas and yellow dust stretching millions of miles across the star-filled darkness. Even the space between planets bears the sun's signature. The solar wind carries our star's magnetic field throughout the solar system, creating a complex web of magnetic connections. Invisible field lines stretching between worlds, connecting the planets to their central star through streams of magnetic energy. When these field lines tangle and reconnect, they release bursts of energy that can affect every world in the solar system. The sun's magnetic field also helps protect us from dangerous cosmic rays that stream in from deep space. High-energy particles from distant stars being deflected by the protective magnetic shield that surrounds our solar system. This invisible barrier works together with Earth's own magnetic field to create a safe haven where life can flourish under the gentle warmth of our neighborhood star. The sun's surface holds secrets that appear and vanish in cycles we're only beginning to understand. Dark patches scattered across the blazing solar surface, each one larger than planet Earth, surrounded by brilliant golden fire. Sunspots mark the places where powerful magnetic fields break through the surface, cooling these regions by nearly 2,000 degrees. What looks like darkness is actually still incredibly hot, about 7,000 degrees Fahrenheit. These magnetic storms on the sun's surface can grow larger than Jupiter in just a few days, then disappear completely within weeks. The largest sunspot ever recorded stretched across more than 80,000 miles of the sun's surface, a colossal dark vortex swirling across the solar surface, its magnetic field lines twisting like invisible tornadoes of pure energy. This giant magnetic storm could have swallowed 13 Earths side by side. Some sunspots appear alone, while others cluster together in complex groups that can span hundreds of thousands of miles. The magnetic fields in these regions become so twisted and tangled that they eventually snap like rubber bands, releasing tremendous bursts of energy into space. Temperature extremes across the sun tell a surprising story. The solar surface glowing at 10,000 degrees, while above it, an ethereal corona shimmers at temperatures exceeding 2 million degrees. The sun's core burns at 27 million degrees Fahrenheit, hot enough to turn any known material surface temperature drops to a relatively cool 10,000 degrees. This creates one of the universe's greatest mysteries. The corona, that ghostly atmosphere surrounding the sun, somehow heats up to more than 2 million degrees as you move away from the surface. Solar flares represent the sun's most violent outbursts of energy, brilliant arcs of plasma erupting from the solar surface, stretching hundreds of thousands of miles into space like luminous bridges of fire. The most powerful flare ever detected released energy equal to billions of hydrogen bombs, exploding every second for hours. These magnetic explosions can accelerate particles to nearly the speed of light, sending them racing across the solar system in minutes. When these high-energy particles reach Earth, they can disrupt radio signals and create auroras visible as far south as the Caribbean. The sun rotates faster at its equator than at its poles, completing one full rotation every 25 days at the middle, but taking 35 days at the polar regions. Swirling bands of plasma flowing at different speeds across the solar surface, creating patterns like cosmic fingerprints in the burning gas. This uneven rotation twists the sun's magnetic field lines like taffy, building up tension that eventually explodes in solar flares and coronal mass ejections. The fastest solar wind particles can travel at speeds of 5 million miles per hour, racing from the sun to Earth in less than 18 hours. Deep within the sun's core, nuclear fusion converts 4 million tons of matter into pure energy every single second. The brilliant heart of the sun, where hydrogen atoms merge in cascades of blinding light, releasing waves of energy that will journey for thousands of years to reach the surface. This energy takes between 10,000 and 170,000 years to work its way from the core to the surface, bouncing between countless atoms in a random walk through the sun's interior. The photons we see today began their journey when early humans were just learning to use fire. The sun's magnetic field extends far beyond what we can see, creating the largest structure in our solar system. Invisible magnetic field lines streaming out from the sun like the spokes of a cosmic wheel, reaching past all the planets into the darkness beyond. This magnetic bubble, called the Heliosphere, stretches more than 11 billion miles from the Sun, protecting our entire solar system from most of the dangerous radiation flowing between the stars. At its outer edge, the solar wind finally meets the interstellar medium, creating a boundary where our sun's influence fades into the vast emptiness between stars. Sometimes the sun whispers before it roars. Solar flares begin as tiny magnetic disturbances, smaller than a city, growing quietly in the sun's atmosphere for hours or even days. Delicate threads of plasma rising from the sun's surface like glowing ribbons, twisted by invisible magnetic forces into graceful arcs against the golden solar atmosphere. These magnetic field lines stretch and bend like rubber bands, storing enormous amounts of energy in their twisted shapes. When they finally snap back into place, they release the power of 10 billion hydrogen bombs in a matter of minutes. The smallest solar flares, called microflares, happen constantly across the sun's surface. Scientists detect thousands of them every day, each one releasing as much energy as a major earthquake on Earth. Tiny bright flashes scattered across the sun's churning surface, like fireflies dancing over a golden ocean, each spark containing the power of lightning storms. These gentle eruptions help heat the sun's outer atmosphere, keeping it mysteriously hotter than the surface below. The corona reaches temperatures of 2 million degrees, while the sun's surface stays at a relatively cool 11,000 degrees. Between the massive flares that make headlines and these tiny microflares lies a whole spectrum of solar activity. B-class flares barely register on our instruments, while C-class flares create small radio blackouts, streams of charged particles flowing away from the sun in elegant spirals, following the curved paths of magnetic field lines like luminous rivers in space. M-class flares can disrupt satellite communications and create beautiful auroras when they reach Earth. The most powerful X-class flares can knock out power grids and force airlines to reroute flights away from the polar regions. Each solar flare follows the same basic pattern, but no two are exactly alike. They begin in active regions where where the sun's magnetic field lines become tangled and twisted. Complex knots of golden plasma suspended above the sun's surface, held in place by invisible magnetic forces, glowing against the deep orange solar atmosphere. These active regions appear as dark sunspots when viewed from Earth, but they're actually cooler areas surrounded by intense magnetic activity. The magnetic field lines above these regions can stretch for hundreds of thousands of miles, creating vast loops and arches of superheated gas. When a flare erupts, it sends 3 different types of energy racing through space. First comes the electromagnetic radiation, traveling at the speed of light and reaching Earth in just 8 minutes. Brilliant white light bursting from the sun's edge like a cosmic flashbulb, sending waves of energy radiating outward into the darkness of space. Radio telescopes on Earth detect this burst immediately, alerting scientists to the flare's intensity and location. Next come the high-energy particles, racing through space at nearly half the speed of light. These particles can reach Earth in 30 to 60 minutes, creating radio blackouts and radiation hazards for astronauts. The slowest component of a solar flare is also often the most spectacular. The coronal mass ejection travels at speeds between 1 and 5 million miles per hour, carrying billions of tons of plasma away from the sun. A massive bubble of glowing plasma expanding through space like a cosmic soap bubble, carrying twisted magnetic field lines and charged particles toward the planets. When this plasma cloud reaches Earth's magnetic field, it can trigger geomagnetic storms that light up the sky with auroras visible as far south as Mexico. Solar flares also create something called solar energetic particle events. These high-speed protons and electrons can penetrate deep into Earth's atmosphere, creating secondary particles that rain down on the planet's surface. Cascades of invisible particles streaming down through Earth's upper atmosphere, creating shimmering curtains of light as they collide with oxygen and nitrogen molecules. Scientists can detect these particles in ice cores from Greenland and Antarctica, creating a record of major solar storms that goes back thousands of years. The sun's flares follow patterns that scientists are still learning to predict. Some active regions produce dozens of flares over several days, while others remain quiet for weeks. The sun's golden surface, marked with dark magnetic regions like spots on a glowing sphere, each one a potential source of explosive energy. The largest flares tend to happen when magnetic field lines with opposite polarities come close together and suddenly reconnect. This process, called magnetic reconnection, converts the stored magnetic energy into kinetic energy and heat almost instantaneously. Even the smallest details of solar flares reveal the sun's incredible complexity. The plasma in a flare can reach temperatures of 50 million degrees, hot enough to strip electrons from iron atoms. Superhot plasma glowing white-hot against the sun's orange surface, twisted into spirals and loops by magnetic forces invisible to the eye. This extreme heat creates X-rays that can only be observed by satellites above Earth's atmosphere. Ground-based telescopes see the flare's visible light and radio waves, but the full spectrum of a solar flare spans from radio waves to gamma rays. Scientists have discovered that solar flares can trigger other flares in a process called sympathetic flaring. When one active region erupts, the shock waves and magnetic disturbances can destabilize other regions hundreds of thousands of miles away. Waves of energy rippling across the sun's surface, like rings spreading from a stone dropped in a golden pond, each ripple carrying the potential for new eruptions. This chain reaction effect shows how interconnected the sun's magnetic field really is, with disturbances in one area affecting the entire solar atmosphere. The vast bubble of charged particles that surrounds our solar system remained hidden from human eyes for centuries. An enormous, invisible sphere of glowing plasma stretching far beyond the planets, its edges shimmering faintly where it meets the darkness of interstellar space. Ancient astronomers could see the sun's light and feel its warmth, but they had no way to detect the constant stream of particles flowing outward in all directions. This solar wind, as we now call it, creates a protective boundary called the Heliosphere that extends roughly 100 times farther from the sun than Earth's orbit. The first hints of this invisible came from studying comets. In the 1600s, astronomers noticed that comet tails always pointed away from the sun, regardless of which direction the comet was traveling. A brilliant comet streaking through the star-filled void, its glowing tail streaming away from the golden sun like luminous silk caught in an invisible wind. This observation puzzled scientists for centuries. If comets were simply chunks of ice and rock, why would their tails behave this way? The answer lay in forces they couldn't yet detect. German astronomer Ludwig Biermann made the connection in 1951. He realized that something invisible must be flowing constantly from the sun, pushing the comet tails outward. Streams of invisible particles radiating outward from the sun in all directions, creating ripples and waves in the fabric of space itself. Biermann called this mysterious flow the solar wind, and he calculated that it must travel at incredible speeds to affect comets so dramatically. His mathematical models suggested the solar wind moved at hundreds of miles per second. The space age finally allowed scientists to measure what Biermann had predicted. In 1959, the Soviet Luna 2 probe became the first spacecraft to detect the solar wind directly. Delicate instruments floating through the void, measuring invisible streams of charged particles that flow like a river of light from the burning sun. The probe's simple particle detectors confirmed that space was not empty, but filled with a thin stream of electrically charged particles. These particles, mostly protons and electrons, had been stripped from the sun's outer atmosphere and accelerated to enormous speeds. American physicist Eugene Parker developed the mathematical framework that explained how the solar wind works. In 1958, he published calculations showing that the sun's corona was so hot that gravity couldn't hold all of its particles. The sun's outer atmosphere glowing like molten gold, with streams of particles breaking free and accelerating into the cosmic darkness beyond. Parker's equations predicted that this escaping material would accelerate as it moved away from the sun, eventually reaching supersonic speeds. Many scientists initially rejected his ideas because they seemed too radical. The Mariner 2 spacecraft proved Parker right in 1962 when it made the first detailed measurements of solar wind during its journey to Venus. A small probe drifting through the solar system, its sensors detecting the invisible hurricane of particles that surrounds all the planets like a vast ocean of energy. The spacecraft found that the solar wind speed varied dramatically, sometimes flowing at 200 miles per second, and other times racing along at 500 miles per second. These variations matched Parker's predictions about how different regions of the sun's atmosphere would contribute to the wind. Scientists gradually realized that the heliosphere acts like a cosmic shield, protecting our solar system from dangerous radiation streaming through interstellar space. A glowing protective bubble surrounding the sun and all its planets, its edges rippling and pulsing as it pushes against the cold currents of interstellar space. Without this barrier, Earth would be bombarded by much higher levels of cosmic rays, potentially making life on our planet far more difficult. The solar wind weakens these incoming particles by creating turbulence and magnetic barriers. The true size of the heliosphere remained a mystery until the Voyager spacecraft began their epic journeys in 1977. Twin spacecraft racing through the outer darkness of the solar system, their instruments detecting the fading whispers of the solar wind as they approach the edge of known space. These robotic explorers carried instruments designed to measure the solar wind's strength and detect the moment when they would cross the boundary into interstellar space. Scientists expected this boundary, called the heliopause, to be somewhere beyond the orbit of Pluto. Voyager 1 finally crossed this invisible frontier in 2012, more than 35 years after its launch. The edge of the heliosphere appearing like a shimmering wall of energy, where the golden glow of solar particles meets the deep purple darkness of interstellar space. The spacecraft's instruments detected a sudden drop in solar wind particles and a corresponding increase in cosmic rays from deep space. This moment marked humanity's first direct contact with the true interstellar medium, the space between the stars. The discovery revealed that our solar system exists within a vast cavity carved out by the sun's influence, an enormous hollow sphere of influence glowing softly in cosmic void, its boundaries constantly shifting and pulsing with the rhythm of solar activity. This protective cocoon has shaped the evolution of life on Earth for billions of years, demonstrating once again how deeply connected we are to the star that lights our days. The protective embrace of our sun's influence extends far beyond what most people imagine. But the surprises don't end at the edge of space. Earth tilted at 23.5 degrees as it orbits the sun. One hemisphere bathed in golden light, while the other rests in shadow. Here on our home planet, the sun creates one of nature's most beautiful illusions. Most people believe that summer arrives because Earth moves closer to the sun during its yearly orbit. This seems logical, but it reveals how even our most basic assumptions about the cosmos can be wrong. Earth actually reaches its closest point to the sun in early January, during the depths of winter in the northern hemisphere, a snow-covered landscape glowing under brilliant sunlight, ice crystals sparkling like diamonds across frozen fields and bare tree branches. The planet sits about 3 million miles closer to our star during January than it does in July. This means that winter in the northern hemisphere occurs when Earth receives slightly more solar energy, not less. The sun appears about 3% larger in our sky during January, casting slightly more intense light on the frozen ground. The true cause of seasons lies in Earth's gentle tilt. Sunlight striking Earth at a steep angle, golden rays spreading thin across rolling hills and valleys, creating long shadows that stretch toward distant mountains. Our planet leans like a spinning top that has begun to wobble, always maintaining the same angle as it travels around the sun. During summer in the northern hemisphere, that part of Earth tilts toward the sun, allowing sunlight to strike the surface more directly. The same amount of solar energy concentrates into a smaller area, warming the land and lengthening the days. The opposite hemisphere tilted away from the sun, receiving slanted rays of light that spread across vast continents, painting them in soft amber hues. Meanwhile, the southern hemisphere tilts away from the sun during this same period, causing winter to settle across those lands. The sun's rays arrive a shallow angle, spreading the same energy across a much larger area. This creates the surprising reality that when children in North America build snowmen in December, children in Australia splash in swimming pools under the summer sun. The sun's light takes the same 8 minutes and 20 seconds to reach both hemispheres, but the angle at which it arrives makes all the difference. Sunlight streaming through Earth's atmosphere at a low angle, creating spectacular bands of orange and pink light that stretch across the horizon. During winter, sunlight must travel through more atmosphere to reach the surface. This longer journey scatters more blue light, leaving the warmer colors to paint the landscape in golden tones. The same physics that creates stunning sunsets also explains why winter sunlight feels gentler on the skin. The Arctic Circle bathed in continuous twilight, the sun hovering just above the horizon, casting everything in ethereal purple and gold light. Near Earth's poles, the planet's tilt creates even more dramatic effects. During summer, regions within the Arctic and Antarctic circles experience continuous daylight for months. The sun traces a complete circle around the sky without ever setting, creating a phenomenon called the midnight sun, a landscape of ice and snow glowing under the midnight sun. The golden orb hanging low in a pale sky, casting long blue shadows across pristine white terrain. 6 months later, these same regions plunge into polar night, when the sun never rises above the horizon. The Aurora borealis dancing across a star-filled sky above a frozen wilderness. Ribbons of green and blue light shimmering against the cosmic darkness. During this extended darkness, the aurora often becomes visible as solar particles interact with Earth's magnetic field high in the atmosphere. The sun continues to influence these polar regions even when its light cannot directly reach them. A forest in autumn with leaves turning brilliant shades of red, orange, and gold. Sunlight filtering through the canopy and creating dappled patterns on the forest floor. The changing seasons also reveal another surprise about how life responds to solar energy. Trees don't simply lose their leaves because of cold temperatures. They begin preparing for winter in response to the changing length of daylight. As days grow shorter, trees stop producing chlorophyll, the green chemical that captures sunlight for energy. Individual leaves transforming from green to vibrant yellow and red, their cellular structure breaking down and revealing hidden pigments that glow like tiny flames. The brilliant reds, oranges, and yellows of autumn leaves were present in the trees all along, masked by the dominant green of chlorophyll. A single maple tree standing in an open field, its canopy ablaze with autumn colors, surrounded by golden grass swaying in gentle breeze. When the tree stops producing this green pigment, the hidden colors emerge like a secret painting revealed. The tree essentially shuts down its solar collection system, preparing to survive the months when the sun's energy becomes too weak and indirect to support active growth. Snow beginning to fall on a landscape of bare trees, their dark branches creating intricate patterns against a gray sky filled with gently drifting snowflakes. Even the timing of snowfall connects to Earth's relationship with the sun. Snow tends to fall most heavily when the temperature hovers near freezing, because slightly warmer air can hold more moisture. The coldest winter days often bring clear, brilliant skies, with sunlight glittering off snow crystals like scattered diamonds. Pristine snow covering a mountain valley, each crystal reflecting sunlight and creating a landscape that sparkles and glows under the bright blue sky. These seasonal rhythms have shaped life on Earth for billions of years, creating the predictable cycles that allow plants and animals to time their growth, reproduction, and migration. A vast migration of birds flying in perfect formation across a sunset sky, their silhouettes dark against clouds, painted in brilliant shades of orange and pink. The sun's steady energy, delivered at different angles throughout the year, provides the reliable foundation that makes complex life possible on our tilted, spinning world. The sun's influence reaches far beyond the simple delivery of light and heat. Brilliant streams of charged particles flowing outward from the sun's surface, creating luminous ribbons of energy that stretch across the darkness of space. Every second, our star releases a constant stream of charged particles called the solar wind. These invisible messengers carry pieces of the sun's own atmosphere across millions of miles, creating an invisible bubble around our entire solar system. When these solar particles collide with Earth's magnetic field, something magical happens in the polar regions. Shimmering curtains of green and blue light dancing across a star-filled Arctic sky. The Aurora Borealis rippling like silk in a cosmic breeze. The aurora appears when solar particles follow Earth's magnetic field lines down toward the poles, where they crash into oxygen and nitrogen atoms in our upper atmosphere. Oxygen creates the familiar green glow at lower altitudes, while nitrogen produces deeper reds and purples higher up. The intensity of these celestial light shows depends entirely on the sun's activity. Massive solar flares erupting from the sun's surface, sending brilliant arcs of plasma thousands of miles into space, glowing orange and white against the black void. During periods of high solar activity, the aurora can appear much farther south than usual. Historical records show aurora visible as far south as Rome and the Caribbean during particularly intense solar storms. These same solar particles that create the aurora also interact with Earth's oceans in subtle but important ways. Deep ocean currents flowing like underwater rivers, carrying warm water from tropical regions toward the polar seas. The water glowing with a soft blue luminescence. The sun's magnetic field influences Earth's magnetic field, which in turn affects the behavior of charged particles in seawater. Some scientists believe this connection might influence ocean circulation patterns over very long time periods. The relationship between solar activity and Earth's climate extends beyond the obvious effects of temperature and seasons. Towering volcanic peaks releasing gentle plumes of steam and ash into a dawn sky painted in soft shades of pink and gold. Solar variations can influence atmospheric pressure patterns, which affect wind currents and weather systems. During periods of low solar activity, certain regions experience different precipitation patterns, influencing everything from crop yields to volcanic activity through complex atmospheric interactions. Tree rings preserve a record of these solar connections, stretching back thousands of years. Ancient tree rings revealed in cross-section each ring glowing with warm amber light, showing decades of growth patterns preserved in the wood. During years of high solar activity, trees often grow faster due to changes in atmospheric chemistry and temperature patterns. Scientists can read these wooden archives to understand how solar cycles have influenced Earth's climate throughout history. Even the behavior of migratory animals connects to solar activity through magnetic field interactions. Vast flocks of birds flying across a twilight sky filled with the soft glow of Aurora, their wings silhouetted against curtains of green and purple light. Many birds and marine animals use Earth's magnetic field for navigation, and solar storms can temporarily disrupt these natural compass systems. Whales sometimes beach themselves during intense solar events, possibly because their magnetic navigation becomes confused. The sun's influence reaches into the depths of our oceans through a process called solar heating of surface waters. Sunlight penetrating the clear blue depths of tropical ocean water, creating shafts of golden light that fade into the mysterious darkness below. This surface warming drives the global circulation of ocean currents, moving warm water toward the poles and cold water toward the equator. Without this solar-driven circulation, Earth's climate would be far more extreme, with scorching equatorial regions and frozen polar zones, bioluminescent plankton glowing like tiny blue stars scattered across the surface of calm ocean water under a starlit sky. Even the microscopic life in our oceans responds to solar cycles. Plankton populations fluctuate with solar activity, influencing the entire marine food chain from tiny fish to massive whales. These connections demonstrate how the sun's energy flows through every level of life on Earth. Massive ice sheets reflecting brilliant sunlight, their pristine white surfaces stretching endlessly toward distant mountains under a deep blue polar sky. The reflection of sunlight from ice and snow helps regulate Earth's temperature through a process called the albedo effect. When ice melts due to warming, darker surfaces absorb more solar energy, creating a feedback loop that connects the sun's energy directly to climate change patterns. Gentle waterfalls cascading down moss-covered rocks in a forest glen, with shafts of sunlight filtering through the canopy, illuminating the mist. The water cycle itself depends entirely on solar energy to lift moisture from oceans and lakes into the atmosphere. Every raindrop, every snowflake, every morning dew contains energy that originated in the sun's core and traveled across 93 million miles to power Earth's weather systems. Rolling hills covered in wildflowers stretching toward the horizon, with storm clouds gathering in the distance and lightning flickering silently between them. Lightning connects to solar activity in ways scientists are still discovering. The electrical charge that builds up in storm clouds may be influenced by cosmic rays from space, which are partly controlled by the sun's magnetic field. When solar activity is low, more cosmic rays reach Earth's atmosphere, potentially affecting cloud formation and storm intensity. Crystal clear mountain lakes reflecting the colors of sunset, their surfaces perfectly still except for gentle ripples spreading outward from a single point. The sun's energy even influences the formation of clouds through complex interactions with atmospheric particles. Solar radiation helps create the tiny particles that water vapor condenses around to form cloud droplets. Without these solar-influenced processes, our planet's water would remain locked in the oceans, and rain would never fall on the land. Vast grasslands swaying in the wind under a sky filled with towering cumulus clouds, their white peaks glowing in the afternoon sunlight. The wind itself owes its existence to uneven solar heating of Earth's surface. Warm air rises from sun-heated regions, while cooler air flows in to replace it, creating the circulation patterns that distribute heat around our planet and make weather possible. Northern lights reflecting off the surface of a frozen lake, creating ribbons of green and blue light, both in the sky above and in the ice below. These connections form an intricate web of relationships that spans from the sun's core to the deepest ocean trenches. Every system influences every other system in a vast, interconnected dance of energy and matter that has continued for billions of years, creating the stable, life-supporting world we call home. This beautiful web of connections exists because our sun remains remarkably stable, burning steady warmth for billions of years. A golden star glowing peacefully in the deep black of space, surrounded by 8 planets orbiting in perfect circles, all bathed in gentle yellow light. But like all stars, the sun changes slowly over time, growing brighter and hotter with each passing million years. Scientists have discovered that our star burns about 10% brighter today than it did when Earth first formed 4.5 billion years ago. This gradual brightening happens because the sun converts hydrogen into helium in its core through nuclear fusion. Brilliant streams of plasma swirling inside a star's core, glowing white-hot with nuclear fire, creating intricate spirals of light and energy. As more helium accumulates in the center, the core becomes denser and hotter, making the fusion reactions run faster and produce more energy. The sun gains about 1% more brightness every 100 million years, a change so slow that entire mountain ranges rise and fall between noticeable increases. Ancient rocks tell us stories of how Earth has adapted to this slowly brightening sun. Layered sedimentary cliffs rising from a primordial ocean, their bands of red and orange stone glowing in the light of a younger, dimmer sun. Early in Earth's history, when the sun was much fainter, our planet stayed warm enough for liquid water because the atmosphere contained more greenhouse gases. Carbon dioxide levels were thousands of times higher than today, trapping heat like a thick blanket around the young Earth. As the sun grew brighter over geological time, Earth's climate systems responded by removing carbon dioxide from the atmosphere. Vast coral reefs growing in shallow tropical seas, their limestone structures gleaming white beneath crystal clear water, slowly pulling carbon from ancient oceans. Ocean creatures began building shells and skeletons from calcium carbonate, locking away carbon in their bodies. When they died, their remains settled to the seafloor, forming limestone deposits that still store carbon today. Plant life also helped balance the sun's increasing brightness by pulling carbon dioxide from the air during photosynthesis. Dense forests of ancient ferns and towering tree ferns covering a misty landscape, their green fronds filtering dappled sunlight in a prehistoric world. Over millions of years, dead plants became coal, and oil deposits, removing even more carbon from the atmosphere. This slow dance between solar brightening and atmospheric carbon created the stable climate that allowed complex life to evolve. The sun's magnetic field also changes over time, following patterns that scientists are still working to understand. Invisible magnetic field lines arcing gracefully from a star's surface, creating luminous loops and spirals of charged particles dancing in the corona. Every 11 years, the sun's magnetic poles flip completely, north becoming south and south becoming north. During these magnetic reversals, sunspot activity reaches its peak and solar flares become more common. But even longer changes occur in the sun's magnetic behavior. A star's surface marked with dark sunspots clustered near the equator, surrounded by bright solar flares reaching out like fiery tentacles into space. Historical records show that sunspot activity nearly disappeared between 1645 and 1715, a period called the Maunder Minimum. During these decades, winters in Europe and North America became unusually harsh, earning this time the nickname, the Little Ice Age. Tree rings from that era reveal shorter growing seasons and colder temperatures across much of the northern hemisphere. Ancient tree rings visible in a cross-section of wood, their narrow bands telling stories of cold summers and harsh winters from centuries past. The sun's reduced magnetic activity during the Maunder Minimum may have allowed more cosmic rays to reach Earth's atmosphere, affecting cloud formation and cooling the planet slightly. These solar changes remind us that our star follows rhythms spanning decades, centuries, and millions of years. Time-lapse view of a star slowly pulsing with light over cosmic time, its surface growing gradually brighter while maintaining the same steady glow. The sun that warmed the dinosaurs was noticeably dimmer than the one that shines on us today. The sun that will warm our planet millions of years from now will burn even brighter still, continuing its patient transformation through the vast reaches of cosmic time. Deep within the sun's core, temperatures reach 27 million degrees Fahrenheit. At these incredible temperatures, hydrogen atoms move so fast they slam together with tremendous force. The sun's blazing core glowing white-hot with nuclear fusion. Streams of pure energy radiating outward through layers of plasma and fire. This collision creates helium and releases pure energy in the form of light. Every second, the sun converts 4 million tons of matter into energy through this process called nuclear fusion. The light created in the core begins a remarkable journey to reach us. Brilliant photons of light bouncing through dense layers of solar plasma. Each particle of light ricocheting countless times through the sun's interior. A single photon of light takes between 10,000 and 1 million years to travel from the sun's core to its surface. The light bounces and scatters through the dense plasma, taking a zigzag path that stretches across eons. Once it finally reaches the surface, that same photon speeds through space and arrives at Earth in just 8 minutes and 20 seconds. The sun creates light in every color of the rainbow. Though we see it as white, when all colors blend together, white sunlight splitting into a perfect rainbow spectrum. Bands of red, orange, yellow, green, blue, and violet light streaming through space. When sunlight passes through water droplets in the air, we see these hidden colors revealed as rainbows. The sun produces more yellow and green light than any other color, which is why our eyes evolved to be most sensitive to these wavelengths. Golden sunlight filtering through Earth's atmosphere, painting the sky in warm amber and honey tones during a peaceful sunset. The sun's surface temperature of 10,000 degrees Fahrenheit gives it a yellowish-white color. Hotter stars burn blue-white, while cooler stars glow orange or red. A brilliant blue-white star blazing in deep space. Its surface so hot it outshines dozens of yellow stars scattered around it. The sun sits perfectly in the middle range of stellar temperatures, burning with a steady, warm light that has remained remarkably consistent for billions of years. Solar light carries the fingerprints of every element forged within the sun's depths. When astronomers spread sunlight through a prism, they see thousands of dark lines crossing the spectrum. Sunlight spread into a detailed spectrum, showing countless thin dark absorption lines, each line revealing the presence of different elements in the sun's atmosphere. Each line represents a specific element, absorbing light at its own unique wavelength. These spectral lines elements tell us the sun contains hydrogen, helium, iron, calcium, sodium, and dozens of other elements. The sun creates heavier elements through fusion, but only up to iron, the periodic table of elements glowing softly, with hydrogen and helium blazing bright, while heavier elements like iron and nickel shine with steady light. Elements heavier than iron require even more extreme conditions to form. When massive stars explode as supernovas, they forge gold, silver, uranium, and other heavy elements in their final moments. The gold in your jewelry and the calcium in your bones were created in the heart of an ancient star that died long before our sun was born. Different layers of the sun's atmosphere glow with different colors. When viewed through special filters, the sun's chromosphere glowing deep red with hydrogen light, wispy prominences arcing gracefully above the solar surface like luminous flames. The chromosphere, a thin layer above the visible surface, glows bright red from hydrogen gas. The corona, the sun's outermost atmosphere, shines with a ghostly white light that extends millions of miles into space. The sun's corona stretching into space like delicate silver streamers, its ethereal glow forming intricate patterns against the star-filled void. The sun's magnetic field creates spectacular light shows in its atmosphere. Solar prominences arch hundreds of thousands of miles above the surface, glowing like enormous bridges of fire. Massive solar prominences arcing high above the sun's surface, glowing loops of plasma, following invisible magnetic field lines through space. These magnetic loops can hold plasma at temperatures of millions of degrees, making them shine brighter than the surface below. When these magnetic structures suddenly snap and reconnect, they release bursts of light and energy that race across the solar system. The light from our sun has traveled an incredible distance to reach your eyes. A single beam of sunlight streaming across 93 million miles of empty space, carrying warmth and energy from the sun to earth. Every ray of sunshine that touches your skin began its journey in the nuclear furnace at the sun's core, traveled for millennia through the star's interior, then crossed the vast emptiness of space to find you. The sunlight falling on Earth today carries the same elements that will one day become part of new stars, new planets, and perhaps new forms of life scattered throughout the galaxy. The sun creates sounds that no human ear could ever hear directly. Yet, instruments can capture these vibrations and transform them into haunting melodies. Massive sound waves rippling across the sun's surface in slow motion, creating visible patterns of light and shadow that pulse rhythmically. The entire star rings like a bell, with acoustic waves bouncing through its interior every few minutes. These solar oscillations make the sun's surface rise and fall by tiny amounts, creating a deep thrumming that scientists can detect and convert into audio. When you listen to recordings of these solar sounds, you hear something that resembles distant thunder mixed with the low hum of a massive organ, the sun's glowing surface undulating gently like golden ocean waves, with bright spots pulsing in rhythm across the stellar sphere. The star breathes with a period of about 5 minutes, expanding and contracting as pressure waves travel from its core to its surface. This stellar heartbeat has been constant for billions of years, a rhythm that predates every mountain on Earth. The solar wind carries its own invisible music across the solar system. Streams of charged particles flowing outward from the sun like luminous rivers, creating shimmering curtains of light in the darkness of space. When these particles interact with planetary magnetic fields, they create electromagnetic waves that instruments can translate into eerie whistles and chirps. Earth's magnetosphere sings with these solar melodies, producing sounds that range from bird-like chirping to deep whale songs. During solar storms, the sun's voice becomes more dramatic. A massive solar flare erupting from the sun's surface, sending brilliant arcs of plasma spiraling into space against a backdrop of swirling magnetic fields. Radio telescopes detect bursts of static and crackling sounds as charged particles race through space at millions of miles per hour. These cosmic radio signals travel at the speed of light, reaching Earth in just 8 minutes and 20 seconds. The sun's magnetic field lines vibrate like the strings of an enormous invisible harp. Invisible magnetic field lines around the sun glowing faintly, stretching and twisting in complex patterns space. When these field lines snap and reconnect during solar flares, they release energy equivalent to billions of nuclear bombs. The electromagnetic pulse from these events creates radio waves that sweep across the solar system like ripples on a cosmic pond. Even the sun's rotation creates a subtle Doppler shift in the sounds it produces. The sun slowly rotating on its axis, with bright active regions and darker sunspots moving across its surface in a stately dance. The equator spins faster than the poles, creating a complex pattern of sound frequencies that scientists can map. This differential rotation is what winds up the sun's magnetic field lines and drives the 11-year solar cycle. Deep within the sun's core, nuclear fusion creates its own acoustic signature. The sun's blazing core, glowing white-hot with nuclear fire, surrounded by layers of increasingly cooler plasma that shimmer with different colors. Every second, the core converts 4 million tons of matter into pure energy, and this process generates pressure waves that travel outward through the star's layers. These waves take hundreds of thousands of years to reach the surface, carrying the sound of creation itself. The sun's corona, that ethereal atmosphere visible during eclipses, has its own unique acoustic properties. The sun's corona, extending millions of miles into space, appearing as delicate streamers and loops of glowing plasma against the star-filled void. The extremely thin gas of the corona can carry sound waves, though they travel much differently than sound waves in Earth's atmosphere. These coronal waves move at speeds of hundreds of miles per second, creating a celestial symphony that plays out on a scale larger than entire planets. When solar particles reach Earth and interact with our atmosphere, they create the sounds of the Aurora, brilliant green and purple Aurora dancing across a dark polar sky, with sheets of light rippling and flowing like cosmic curtains. People in the far north sometimes report hearing crackling or hissing sounds during intense aurora displays. Scientists believe these sounds come from electrical discharges in the air, created when solar particles collide with gas molecules high above our heads. The sun's ancient light carries within it the memory of sounds that echoed through space billions of years ago. Ancient ancient starlight streaming across vast distances, carrying the energy and elements forged in stellar cores throughout cosmic time. Every photon of sunlight began its journey in the nuclear furnace of the sun's core, where the sounds of fusion reactions have been playing the same deep notes for nearly 5 billion years. A cosmic symphony that connects us to the very beginning of our solar system. The mathematics of our solar system reveals patterns so perfect they seem almost planned. Earth floating in the perfect orbital zone around a golden sun, neither too close nor too far, bathed in gentle warm light. Earth sits at exactly 93 million miles from the sun, a distance astronomers call 1 astronomical unit. This measurement becomes the ruler for our entire solar system. Mars orbits at 1.5 astronomical units. Jupiter sits at 5.2. The numbers create a rhythm, a mathematical dance that has played out for billions of years. The speed of Earth's orbit follows laws discovered by Johannes Kepler 4 centuries ago. A luminous orbital path tracing Earth's elliptical journey around the sun, glowing like a golden ribbon in the darkness of space. Our planet travels at 67,000 miles per hour, fast enough to circle the entire Earth in just over 22 minutes. Yet this incredible speed feels perfectly still to us. The mathematics ensure we maintain the ideal distance from our star. Too close, and our oceans would boil away. Too far, and they would freeze solid. Scientists call this perfect zone the Goldilocks zone, where conditions are just right for liquid water, the habitable zone around a bright yellow star, shown as a glowing green band where planets could support liquid water. The zone around our sun stretches from about 0.9 to 1.7 astronomical units. Earth sits comfortably within this range, but the margins are smaller than they appear. If our planet moved just 5% closer to the sun, we would lose our water to space. Move 15% farther away, and we would become a frozen world like Mars. The sun's energy output follows mathematical rules that govern all stars. Streams of golden energy radiating outward from the sun's surface in perfect geometric patterns, creating luminous rays across space. Every second, Our star converts 4 million tons of matter into pure energy. This follows Einstein's famous equation, where mass becomes energy at the speed of light squared. The numbers are staggering, yet they remain constant year after year. The Sun has maintained this steady output for nearly 5 billion years, providing the stable energy that life on Earth requires. The orbit itself follows an elegant ellipse, with the Sun positioned at one focus point. Earth's elliptical orbital path, drawn as a glowing curve through space, with the Sun as a brilliant focal point off-center. Earth comes closest to the Sun in early January at about 91.4 million miles. We reach our farthest point in early July at 94.5 million miles. This 3 million mile difference affects the intensity of sunlight by only 6%. The small variation helps moderate Earth's climate rather than creating extreme seasons. The tilt of Earth's axis creates our seasons through pure geometry. Earth tilted at its 23.5 degree angle, with the northern hemisphere bathed in bright sunlight, while the southern hemisphere rests in gentler light. Our planet leans at 23.5 degrees, a precise angle that gives us spring, summer, fall, and winter. Without this tilt, every day would be the same length everywhere on Earth. The equator would always be hot, and the poles would remain forever frozen. The mathematics of this tilt create the changing seasons that have shaped life on our planet for millions of years. Solar radiation follows the inverse square law, one of nature's most fundamental mathematical relationships. Sunlight spreading outward in perfect geometric rays, growing fainter with distance, illuminating planets at different orbital positions. Double the distance from the Sun, and you receive 1/4 the energy. This simple rule explains why Mars receives only 43% of the sunlight that Earth does. Venus, closer to the Sun, receives nearly twice as much. The mathematics are precise and unforgiving. They determine which worlds can support atmospheres, liquid water, and ultimately, life itself. The Sun's 11-year cycle follows mathematical patterns that scientists can predict decades in advance. The Sun's magnetic field lines twisting and reorganizing in brilliant loops of plasma, creating complex geometric patterns of energy. Sunspot numbers rise and fall in waves that match mathematical models. The cycle affects space weather, satellite communications, and even Earth's climate in subtle ways. The precision of these predictions shows how mathematical laws govern even the most complex stellar behaviors. Our star operates like a vast clockwork mechanism, following rules written in the language of mathematics across the infinite darkness of space. The delicate balance that keeps our world alive depends on countless variables working in perfect harmony. Earth floating in the cosmic void, wrapped in a thin blue atmosphere, golden sunlight illuminating one hemisphere, while the other rests in gentle darkness. Our atmosphere is incredibly thin, just 60 miles from the surface to the edge of space. If Earth were the size of an apple, our protective air would be thinner than the apple's skin. This fragile shell of gases shields us from deadly radiation and keeps our planet's temperature stable. The exact distance between Earth and the Sun creates what scientists call the habitable zone. 3 planets orbiting a bright yellow star, one frozen and white, one blue and green with swirling clouds, one red and barren, each receiving different amounts of golden light. Move Earth just 5% closer to the Sun, and our oceans would boil away like Venus. Move us 1% farther out, and we would freeze solid like Mars. The margin for error is remarkably small. This precise positioning has remained stable for billions of years, allowing life to flourish. The Sun's energy output varies by only 0.1% during its 11-year cycle. The Sun's surface rippling with magnetic storms, bright flares erupting in graceful arcs, the star's light pulsing gently with subtle changes in brightness. Even this tiny variation affects Earth's climate. During periods of low solar activity, our planet cools slightly. During active periods, temperatures rise. Scientists can read these changes in tree rings, ice cores, and coral reefs. Each ring in an ancient tree tells the story of that year's solar energy. The magnetic field that surrounds our planet acts like an invisible shield. Earth's magnetic field lines streaming outward in elegant curves, deflecting streams of charged particles from the Sun. creating a protective bubble around the blue planet. Without this magnetic protection, solar wind would strip away our atmosphere grain by grain. Mars lost most of its atmosphere this way when its magnetic field weakened billions of years ago. Our magnetic field flips every few 100,000 years, and during these reversals, we become more vulnerable to cosmic radiation. The moon's gravitational pull stabilizes Earth's tilt at 23.5 degrees. The moon hanging in space near Earth, its gray surface cratered and ancient, tidal forces stretching invisibly between the two worlds like gentle threads of energy. Without our large moon, Earth would wobble chaotically. Our poles might sometimes point directly at the sun, creating extreme seasons that would make complex life nearly impossible. The moon also creates tides that may have helped early life move from ocean to land. Carbon dioxide levels in our atmosphere must stay within a narrow range. Ancient forests of towering trees stretching to the horizon, their leaves capturing sunlight and releasing oxygen, while their roots anchor deep into rich brown soil. Too little, and plants cannot photosynthesize. Too much, and greenhouse heating runs away like on Venus. For the past few billion years, life itself has helped regulate these levels. Plants remove carbon dioxide and produce oxygen. Ocean organisms build shells that lock carbon away in limestone. The sun's position in our galaxy also matters for habitability. The Milky Way galaxy, seen edge-on, a brilliant disk of stars with spiral arms, our solar system, positioned in a quiet region between the bright spiral arms. We orbit in a relatively quiet zone between spiral arms, away from the intense radiation of massive star clusters. If we lived near the galactic center, deadly radiation would sterilize our planet. If we lived in the outer regions, heavy elements needed for rocky planets would be too rare. Even the sun's steady burning depends on precise nuclear physics. The sun's core glowing with intense fusion reactions, hydrogen atoms colliding and merging in brilliant flashes of energy, creating helium and pure light deep within the star. The strong nuclear force must be exactly strong enough to bind protons together despite their electrical repulsion. If this force were slightly weaker, stars could not shine. If it were slightly stronger, all hydrogen would have burned up shortly after the Big Bang. Water exists as a liquid on Earth's surface because of this careful balance. Ocean waves rolling gently under golden sunlight, steam rising from the warm surface, while ice crystals form in the cold upper atmosphere, the water cycle flowing endlessly. The temperature range where water stays liquid is narrow compared to the vast scales of space. Most worlds are either too hot or too cold for liquid water to exist. Our planet sits in the perfect spot where water can flow, evaporate, and freeze in an endless cycle that distributes heat around the globe. This remarkable stability has persisted for over 4 billion years, creating the conditions where life could emerge and evolve into the rich diversity we see today. Yet, for all our centuries of watching the sun, mysteries still dance just beyond our understanding. The sun's corona stretching into space like ghostly silver flames, far hotter than the surface below, glowing with ethereal light against the black void. The corona burns at temperatures over 2 million degrees, while the sun's visible surface stays at a relatively cool 11,000 degrees. Scientists call this the coronal heating problem. Something heats the corona to these incredible temperatures, but we still don't know exactly what. Magnetic field lines twist and snap in the corona's thin gas. Invisible magnetic field lines arcing high above the sun's surface, glowing plasma, following their curved paths like luminous ribbons in space. These magnetic fields carry enormous energy, and when they reconnect and break apart, they might release the heat that makes the corona so blazingly hot. But the precise mechanism remains hidden from our instruments. The sun's magnetic field itself presents another puzzle. Deep inside the sun, flowing currents of plasma create this magnetic field through a process called the dynamo effect. The sun's interior glowing with swirling currents of golden plasma. Invisible magnetic forces threading through the flowing material like streams of energy. But the exact details of how this dynamo works escape our complete understanding. The sun's magnetic field flips every 11 years, yet we cannot predict exactly when these reversals will happen. Solar wind carries particles away from the sun at speeds of nearly 1,000,000 miles per hour. Streams of charged particles flowing outward from the sun like invisible rivers, carrying magnetic fields through the dark emptiness between planets. This wind shapes the magnetic environments of all the planets, but we still struggle to predict exactly how it will behave. Space weather forecasting remains more art than science. The sun's core presents its own mysteries. Nuclear fusion reactions deep inside should produce particles called neutrinos. The sun's core burning with intense fusion fire. Invisible neutrinos streaming outward through layers of dense plasma and rock. For decades, detectors on Earth found only about 1/3 of the expected neutrinos. This neutrino problem puzzled scientists until they discovered that neutrinos can change their identity as they travel. The missing neutrinos were there all along, just wearing different disguises. Yet questions remain about the core's exact temperature and pressure. Layers of the sun's interior glowing in different shades of gold and orange, each zone burning at different temperatures, energy slowly working its way outward. Computer models predict these conditions, but we cannot send instruments to measure them directly. The journey from the core to the surface takes light thousands of years as it bounces between particles. The sun's surface features continue to surprise us. Granules of hot gas bubble up from below in patterns that look like boiling water. The sun's surface covered in bright granules of plasma, each cell glowing like molten gold, dark lanes between them where cooler gas sinks back down. Each granule spans about 600 miles and lasts only about 10 minutes. The exact physics of how these granules form and disappear still challenges our understanding. Sunspots appear and vanish in cycles we can observe, but cannot fully predict. Dark sunspots dotting the sun's golden surface, magnetic field lines twisted into complex knots, surrounded by bright plasma flowing in elegant patterns. Sometimes the sun goes through periods with almost no sunspots at all. The Maunder minimum from 1645 to 1715 saw virtually no sunspot activity. We don't know if such quiet periods will happen again or what triggers them. The sun's rotation adds another layer of mystery. The equator spins faster than the poles, completing one rotation in about 25 days, while the polar regions take 35 days. The sun rotating slowly in space, its equatorial regions glowing brighter as they spin faster than the darker polar areas. This differential rotation winds up the magnetic field lines like rubber bands being twisted. Eventually, these twisted fields break through the surface and create the complex magnetic structures we see. Solar flares release energy equivalent to billions of nuclear bombs in just minutes. A brilliant solar flare erupting from the sun's surface, streams of glowing plasma arcing high into space, magnetic field lines snapping and reconnecting. We can observe these flares and measure their effects, but predicting exactly when and where they will occur remains beyond our current abilities. Each flare represents a sudden release of magnetic energy that has been building up over days or weeks. The sun's influence extends far beyond what we can see. The heliosphere stretching through interstellar space like a vast bubble. The sun's influence reaching far beyond the orbits of the planets. This invisible boundary where solar wind meets interstellar space shifts and changes with the sun's activity. We are only beginning to understand how the sun interacts with the galaxy around us. Even the sun's age presents subtle mysteries. We know our star formed about 4.6 billion years ago, but the exact sequence of events that created it from a collapsing cloud of gas and dust remains unclear. A vast nebula of gas and dust slowly collapsing under its own gravity, swirling currents, forming spiral patterns as the material falls inward toward a bright central glow. Computer simulations show us possible scenarios, but each model makes different assumptions about the initial conditions. These mysteries remind us that the sun, despite being our closest star, still holds secrets waiting to be discovered. Every space mission and ground-based telescope reveals new details that challenge our understanding and open fresh questions about how our nearest star truly works. The sun will not burn forever. In about 5 billion years, our star will begin its final transformation. A brilliant yellow star slowly expanding, its outer layers glowing red and orange as they stretch far beyond their current boundaries. The hydrogen fuel in the sun's core will eventually run out. When that happens, the core will contract while the outer layers expand dramatically. Our sun will become a red giant star. During this red giant phase, the sun will grow enormous. A massive red giant star dominating the sky. Its crimson surface stretching across space where Earth's orbit once existed. The sun's outer edge will reach beyond Mercury's current orbit. It may even engulf Venus and possibly Earth. The temperatures on any remaining planets will soar beyond anything we can imagine. The oceans will boil away into space. The atmosphere will be stripped from our world. But this dramatic expansion will not last forever. Glowing layers of gas and plasma drifting away from a central white dwarf, creating colorful nebula clouds in deep space. The sun will eventually shed its outer layers in gentle waves. These expelled gases will form a beautiful planetary nebula. At the center, a small white dwarf star will remain. This white dwarf will be about the size of Earth, but contain most of the sun's original mass. The white dwarf will be incredibly hot at first. A brilliant white dwarf star glowing intensely against the darkness, surrounded by expanding rings of luminous gas in blues and greens. It will shine with the stored heat from billions of years of nuclear fusion. But without new fuel to burn, it will slowly cool down over trillions of years. The white dwarf will gradually fade from white to yellow to red to brown. Long before the sun dies, other changes will reshape our solar system. Jupiter and Saturn slowly drifting outward through space, their moons covered in thick layers of ice, distant stars twinkling in the background. The outer planets will migrate to different orbits. Jupiter and Saturn will move farther from the sun. Their moons may become frozen worlds in the growing cold. The galaxy itself will change dramatically over these vast timescales. Two spiral galaxies slowly merging together, their spiral arms stretching and twisting as they dance through space. In about 4 billion years, our Milky Way galaxy will collide with the Andromeda galaxy. This cosmic collision will create a new, larger galaxy. The night sky will look completely different. New star formation regions will light up across the merged galaxy. Even as old stars die, new ones will continue to form. Bright young young stars igniting within a colorful nebula, their blue-white light illuminating surrounding clouds of gas and dust. The gas and dust, expelled by dying stars like our sun, will provide the raw materials for future generations of stars. Some of these new stars will have their own planets. Life might emerge on worlds we cannot yet imagine. The universe will keep expanding and cooling. Distant galaxies slowly moving away from each other through the vast darkness, their light growing redder as space itself stretches. Star formation will gradually slow down as the universe ages. But for many billions of years to come, new stars will still ignite in nebulae throughout the cosmos. Our sun's death will not be violent like a supernova, a peaceful white dwarf star glowing softly in space, surrounded by the fading remnants of a colorful planetary nebula. Instead, it will be a gentle release of energy built up over its entire lifetime. The elements forged in the sun's core will drift through space. Carbon and oxygen created by nuclear fusion will eventually become part of new worlds. The iron in future planets will come from more massive stars that explode as supernovae. A brilliant supernova explosion lighting up a distant galaxy. Shockwaves of energy and matter expanding outward in all directions. But the lighter elements that make up much of our solar system will trace their origins back to stars like our sun. Every atom of carbon in future life forms may have spent billions of years in a star's burning core. Even after the sun becomes a cold white dwarf, it will not disappear completely. A dim brown dwarf, star barely glowing in the darkness, its faint light reflecting off nearby asteroids and cosmic debris. White dwarf stars can persist for trillions of years. They cool so slowly that the universe is not yet old enough for any white dwarf to have completely faded away. Our sun's remnant will outlive countless generations of newer stars. The solar system's story will continue long after the sun's nuclear fires go out. Ancient asteroid belts slowly orbiting a faint white dwarf. The rocky debris still following the same paths they traced when the sun burned bright. Asteroids and comets will still orbit the white dwarf remnant. Some of Jupiter's moons might survive as frozen worlds in the outer system. The dance of gravity will continue even when the music of fusion has ended. This distant future reminds us that change is the only constant in the universe. A serene cosmic vista showing multiple generations of stars in different stages of life, from bright blue giants to fading red dwarfs. Stars are born, live their lives, and pass away. But their deaths create the conditions for new stars to form. The cycle of stellar birth and death has been repeating for over 13 billion years. It will continue long after our sun joins the ranks of stellar ancestors, contributing its own elements to the endless story of cosmic renewal. The sun belongs to a generation of stars that astronomers call population. These are relatively young stars, rich in heavy elements created by earlier generations of stellar ancestors. A magnificent spiral galaxy with glowing spiral arms, countless young blue stars scattered throughout, older golden stars forming the central bulge, cosmic dust lanes threading between stellar nurseries. Our sun formed from a cloud that contained the ashes of stars that died billions of years ago. The carbon in our bodies, the oxygen we breathe, the iron in our blood. All of these elements were forged in the nuclear furnaces of ancient stars that exploded long before our solar system existed. This cosmic recycling program has been running for over 13 billion years. The very first stars contained only hydrogen and helium, the simplest elements created in the Big Bang. Primordial gas, clouds glowing faintly in the early universe, vast sheets of hydrogen and helium, illuminated by the first generation of massive blue stars. These pioneer stars lived fast and died young, exploding as supernovae that scattered heavier elements into space. Each generation of stars has built upon the chemical legacy of those that came before. The sun sits in a quiet neighborhood of the Milky Way, about halfway between the galaxy's center and its outer edge. The Milky Way galaxy seen edge-on, a brilliant central bulge surrounded by a thin disk of stars, spiral arms glowing with stellar nurseries, our sun's position marked by a gentle golden glow. This location has been for life on Earth. Closer to the galactic center, deadly radiation from the supermassive black hole and frequent supernovae would sterilize any planets. Too far out, there wouldn't be enough heavy elements to form rocky worlds like Earth. Our star moves through the galaxy at about 220 kilometers per second, carrying the entire solar system with it. A serene view of the Sun and its planetary family moving through the galaxy, trailing streams of solar wind. Distant background, stars slowly shifting position over cosmic time. The Sun completes one orbit around the Milky Way every 225 million years. This means that since Earth formed, our planet has traveled around the galaxy about 20 times. Dinosaurs lived during a different galactic season than we do today. The Sun's position in the galaxy also places it within what scientists call the galactic habitable zone. A cross-section view of the galaxy showing the habitable zone as a glowing ring, neither too close to the dangerous center nor too far from the star-forming regions. This is the region where conditions are just right for complex chemistry and stable planetary systems. Too close to the center brings chaos. Too far away brings isolation and a lack of the heavy elements needed for rocky planets. From the perspective of cosmic time, our Sun is middle-aged, but still has billions of years ahead of it. A time-lapse view of stellar evolution showing multiple generations of stars, from bright blue giants burning quickly to long-lived red dwarfs glowing steadily for trillions of years. The universe is only 13.8 billion years old, and the Sun will continue shining for another 5 billion years. By the time our star becomes a red giant, the universe will be nearly twice as old as it is today. This vast timescale puts human existence into perspective. Earth orbiting peacefully around the Sun, the blue marble suspended in the gentle glow of solar radiation, clouds swirling over continents and oceans. All of recorded human history spans less than 10,000 years. The Sun has been shining steadily for 4.6 billion years. From the Sun's perspective, human civilization is like a single heartbeat in a very long life. The Sun connects us to the deepest patterns of the universe. Every atom in our bodies was created either in the Big Bang or in the core of a dying star. Glowing stellar cores where nuclear fusion creates heavy elements. The intense heat and pressure transforming simple hydrogen into carbon, oxygen, and iron. The calcium in our bones came from exploding stars iron in our blood was forged in stellar furnaces. We are literally made of star stuff, carrying the legacy of cosmic evolution within our very cells. The energy that powers all life on Earth comes from nuclear fusion, happening 150 million kilometers away. The sun's core blazing with nuclear fusion, hydrogen atoms combining to form helium, releasing tremendous energy that will take thousands of years to reach the surface. Photons created in the sun's core begin a long journey outward, bouncing randomly through the dense interior for thousands of years before finally escaping into space. The sunlight touching your face today began its journey in the sun's core when human civilization was just beginning. This energy drives the water cycle, powers photosynthesis, creates weather patterns, and maintains the delicate balance that makes Earth habitable. Sunlight streaming through Earth's atmosphere, illuminating swirling cloud formations, ocean currents carrying warm water across the globe, green forests converting light into life. Remove the sun, and Earth would freeze solid within days. The interconnected web of life depends entirely on our star's steady nuclear burning. The sun also protects us in ways we rarely consider. Its powerful magnetic field and solar wind create a bubble around the solar system called the heliosphere. The invisible heliosphere surrounding the solar system, a vast bubble of solar wind deflecting dangerous cosmic rays and interstellar particles. This cosmic shield deflects most of the high-energy particles that stream through interstellar space. Without the sun's protection, Earth would be bombarded by deadly cosmic radiation. Looking toward the far future, the sun will eventually run out of hydrogen fuel in its core, the sun swelling into a red giant star, its outer layers expanding beyond Earth's orbit, glowing orange and red against the darkness of space. When that happens in about 5 billion years, it will expand into a red giant, potentially engulfing the inner planets. But this stellar death will also enrich space with the heavy elements created during the sun's lifetime, providing raw materials for future generations of stars and planets. The story of the sun is the story of the universe itself, matter, organizing into increasingly complex structures, energy flowing from hot regions to cold ones, and the endless cycle of creation and destruction that has been playing out for billions of years. A cosmic panorama showing the birth, life, and death of stars across cosmic time, nebulae glowing with newborn stars, while ancient white dwarfs fade slowly in the distance. Our sun is both unique and utterly typical, one of hundreds of billions of stars in our galaxy alone. In the vast symphony of the cosmos, the sun plays its part with quiet dignity. The Milky Way galaxy, in all its glory, spiral arms glowing with stellar light. Our sun just one golden point among countless others, all moving together in the cosmic dance. It burns steadily, provides energy for life, and will continue doing so long after our current concerns have been forgotten. This perspective offers a kind of peace. We are part of something much larger than ourselves, connected to the stars and planets through the fundamental forces that shape the universe. The sun's story stretches across deep time, a tale written in nuclear fire and magnetic fields. A golden sun burning steadily in the cosmic void, solar flares dancing around its edges, deep space filled with distant stars twinkling like diamonds. 5 billion years from now, when our star begins its final transformation, the Earth will have witnessed countless sunrises and sunsets. Seasons will have painted the planet in endless cycles of green and gold, white and brown. The ocean tides will have risen and fallen millions of times, shaped by the moon's gentle pull and the sun's warming touch. Ancient Earth covered in primordial oceans, volcanic islands rising from steaming waters, the young sun glowing brightly overhead in a sky filled with cosmic dust. Life on Earth has already survived for nearly 4 billion years under the sun's steady gaze. Single cells learned to capture sunlight and turn it into energy. Plants spread across the continents, filling the air with oxygen. Animals evolved to see the colors of sunrise and feel the warmth of summer afternoons. A lush prehistoric forest with towering ferns and ancient trees. Golden sunlight streaming through the canopy, creating pools of warm light on the forest floor. Every creature that ever lived drew its energy from the sun, either directly or through the food webs that connect all living things. The sun's light carries information across the solar system, telling stories of nuclear reactions that happened deep in its core. Brilliant solar wind streaming away from the sun in all directions. Glowing particles flowing past the planets like luminous rivers in space. Photons that began their journey in the sun's heart 8 minutes ago now warm your face and power the plants around you. The same fusion process that lights our days also creates the elements that make up our bodies. We are literally made of star material, forged in the nuclear furnaces of ancient suns that lived and died before our own star was born. A vast nebula glowing with the remnants of an ancient supernova. New stars beginning to form in the colorful gas clouds. Cosmic recycling on a massive scale. The sun will continue burning hydrogen for another 5 billion years, maintaining the delicate balance that keeps Earth's climate stable. During this time, the continents will drift to new positions. Mountain ranges will rise and erode away. New species will evolve while others fade into extinction. Distant future Earth with unfamiliar continents. The sun appearing slightly larger and brighter in an alien sky. Vast oceans reflecting golden light. Through all these changes, the sun will keep shining, providing the energy that drives weather patterns, ocean currents, and the great cycles of life. The sun's corona extending millions of miles into space. Ghostly streamers of plasma flowing outward, creating the solar wind that fills the entire solar system. When astronomers look at other stars in our galaxy, they see suns at every stage of their lives. Some are young and hot, burning through their fuel quickly. Others are old and cool, slowly fading after billions of years of steady burning. A star-forming region in deep space. Young blue giants and older red stars scattered among glowing gas clouds, each at a different stage of stellar evolution. Our sun sits comfortably in the middle range, neither too young nor too old, burning at just the right rate to support complex life on nearby planets. The magnetic fields that create sunspots and solar flares follow patterns that scientists are still learning to predict. The sun's magnetic field lines visualized as glowing threads wrapping around the solar surface, creating complex loops and spirals of energy. These magnetic storms affect satellites and power grids on Earth, reminding us that we live inside the sun's extended atmosphere. The solar wind that flows past Earth carries magnetic energy all the way to the edge of the solar system, creating a vast bubble called the Heliosphere. The Heliosphere stretching far beyond Pluto's orbit. A massive bubble of solar influence, protecting the inner planets from cosmic radiation. This invisible shield protects us from high-energy particles that stream through interstellar space. Jupiter and Saturn glowing softly in the outer solar system, their many moons catching faint sunlight, the sun appearing as a bright star in their distant skies. Even at the outer edges of the solar system, the sun's gravity keeps comets and asteroids in their long, slow orbits. Some of these icy wanderers take thousands of years to complete a single trip around the sun, spending most of their time in the cold darkness beyond Neptune. A distant comet approaching the inner solar system, its tail beginning to glow as solar heat vaporizes ice and dust, creating a luminous trail millions of miles long. When they swing close to the sun, they develop brilliant tails that can stretch across the entire sky as seen from Earth. The sun's energy drives every weather system on our planet. Massive hurricane systems swirling over Earth's oceans, powered by solar energy. Clouds forming spiral patterns hundreds of miles across. Sunlight evaporates water from the oceans, which rises to form clouds and eventually falls as rain or snow. This water cycle has been operating for billions of years, carving canyons, filling lakes, and providing the fresh water that life depends on. A towering thunderstorm at sunset, lightning flickering inside dark clouds, while the sun's golden light illuminates the storm from behind. The temperature differences created by uneven solar heating drive the winds that circle the globe, mixing the atmosphere and distributing heat from the equator toward the poles. The northern lights dancing across a star-filled sky, green and blue curtains of light shimmering above a snow-covered landscape, powered by solar particles interacting with Earth's magnetic field. The sun's 11-year cycle affects Earth's climate in subtle ways that scientists are still studying. During solar maximum, when sunspot activity peaks, slightly more energy reaches Earth. During solar minimum, the sun's output drops by a tiny fraction. The quiet sun during solar minimum, its surface smooth and unmarked by sunspots, burning steadily with a calm, even glow. These small changes can influence weather patterns, though Earth's thick atmosphere buffers most of the variation. As the sun ages, it will gradually grow brighter and hotter. The sun in the distant future appearing larger and more orange, its outer layers beginning to expand as it evolves toward its red giant phase. In about 1 billion years, the increasing solar output will make Earth's oceans begin to evaporate. Long before the sun becomes a red giant, our planet will become too hot for liquid water to exist on the surface. Future Earth as a dry, rocky world with no oceans, the evolved sun glowing intensely in a pale sky, all water having escaped to space. This seems impossibly far away, but it represents the natural progression of stellar evolution that affects every star in the universe. The elements created in the sun's core will eventually be scattered through space when the star sheds its outer layers, a beautiful planetary nebula glowing with ionized gas, the remnant of a dying star, creating new elements that will someday form planets around younger stars. These materials will become part of new star systems, continuing the cosmic cycle of death and rebirth that has been operating since the first stars formed. A stellar nursery where new stars are being born from the scattered remains of ancient supernovae, glowing gas clouds, condensing into bright young suns. The carbon in our bodies, the oxygen we breathe, and the iron in our blood were all created inside dying stars and scattered through space to eventually become part of planets like Earth. Looking up at the night sky, we see the sun's siblings scattered across the galaxy. The Milky Way arching overhead on a clear night. Billions of stars creating a luminous river across the dark sky. Our sun's stellar family spread across the cosmic landscape. All these stars formed from the same giant molecular cloud that collapsed to create our solar system. Over billions of years, their orbits around the galaxy have carried them far from their birthplace, a vast molecular cloud in space where stars are forming dark lanes of dust silhouetted against glowing gas, the stellar nursery where our sun was born long ago. Some of these stellar siblings might have planets of their own, worlds where other forms of life could be looking up at their own suns and wondering about their place in the universe. The sun connects us to the deepest patterns of the cosmos, galaxies scattered across the observable universe, each containing billions of stars like our sun, cosmic islands of light floating in the vast darkness of space. Every sunrise reminds us that we live on a planet orbiting an ordinary star in an unremarkable galaxy. Yet, we are part of something magnificent and ongoing. A peaceful blue planet seen from orbit at twilight. A thin glowing atmosphere curving along the horizon. Stars filling the vast dark sky above. A crescent moon in the distance, luminous and serene, fantasy art style, dreamy and majestic. The sun will continue its steady burning long after our current worries have faded into history, a constant presence in an ever-changing universe. If this helped you relax tonight, tap like and subscribe. Tomorrow night, we explore something just as incredible. Sweet dreams.